Welcome again, everybody, after the coffee break. I hope the people online have a coffee also. This presentation, we are going to follow with the I/O tools we have. Specifically in Ad-hoc, we have three ad-hoc file systems. In this session, we have two. One is Gecko that we saw, and the other one that we are going to see is Hercules. Hercules is again an ad-hoc file system that can be deployed with the applications, and it's basically a parallel distributed file system that is mostly running in memory. Okay, so we have designed the system running in memory. It can be used as a memory storage for temporal data, or as a bus buffer to optimize the I/O for other applications very easily. And of course, you can use it for all the intermediate operations by downloading data, uploading data from the persistent storage, and downloading data for to the persistent storage at the end. Okay. The good things of Hercules is that it's very nice to run with workflows when you need to communicate things on different steps of the jobs. So you can easily connect the different stages of the workflows to using Hercules without many problems. Okay. Of course, like in Gecko, we are using the highest speed connection in the network, the highest speed we have, and we have implemented instead of using MPI or RPCs, we decided to go to a lower level, where is UCX, and we are using UCX directly for the communication in the file system. In Hercules, we have separate management of data and metadata. Basically, metadata is very loosely managed, but we have metadata servers. Like, for example, in the other file system span, we don't have metadata servers. We rely directly on the hashing and the names of the data set. In here, we have metadata servers, and the metadata servers and the data servers can be deployed, replicated to increase performance, as we are going to see. And of course, all the clients are heavily multi-threading, and they can communicate in parallel with the multiple storage servers. However, to promote scalability, we don't have a one-thread server relation, because in that case, we will need a lot of threads. But we have a pool of threads working. We don't have a collector in the client's library running data collection to send to the servers. We use UCX to pack all the data and send the data back to the servers. One question with Hercules is that we can extend to all the compute nodes without any problems. And the drawback with Hercules is that we are limited right now by the memory size. Why? Because we are living in memory. So the maximum capacity we can use is the available memory size in the node right now. Okay, we are working on a mechanism to make a snapshot of the client buffers in the client node, and in that case, we should be able to download the data, flash the data to the persistent storage in case we need it. Okay, so for that situation, we could use probably the facilities for the just-in-time download to the server using a score and the other facilities we have seen before with Mark. Okay, so the idea is that we are going to connect Hercules, Span, and Gecko in the same pipeline, and at the end we will use a score and cargo to move data in and out. One of the things we have addressed in Hercules is that we can try to work and run the test with a small access size and large access size. I mean, most of the parallel file systems and most of the HPC applications are taught to write a lot and in big chunks. The problem now is that we have new applications like I/O applications that in some cases are writing very, very small accesses in a very high frequency, and this is very important to cover. Okay. So basically, as I said, we have ad-hoc in-memory storage Initially, we are ephemeral, so if we don't do anything to move data to the servers, to the persistent parallel file system servers, our data is volatile, will die with the Hercules system, not with the application, depending on the development and the deployment, sorry. And as I said, we have a distributed basically key-value store. So for us, we have data sets in the system. The data set is divided in chunks, and each chunk has a key. So if we are using files, traditional files, the value is the block, and the key is a key we produce with the container block and the address of the server and some other data, so that we are able to locate easily all the data. Using this approach, we can execute other applications and not traditional file systems. Okay, in Admire, we are working with traditional files because basically we are working with POSIX applications, but using this approach, we can use another interface that we have that basically is a get-set interface, and using the get-set interface, we can store basically everything in a kind of object store way. This is the API we have. We have several kind of APIs, as we are going to see. We can use Fuse, we can use POSIX using preload of the library to intercept the system calls, and we have our native interface with set, get, and set facilities, so that you can write your native applications on top of the file system without using any kind of preload or similar. To facilitate the execution of different applications with different requirements, we have several data distribution policies. Okay, typically in Admire, because of the applications we have, we are using round robin, as we're going to see, but we have other policies depending on hashing and random, another kind of data distribution that can be better to avoid congestion, interference, or some other things. Of course, the system is open source. You can get the source code in the Admire webpage. And we have implemented POSIX. Right now, we have implemented a lot of calls. Actually, I never thought that POSIX has so many calls. We are now around 100 system calls. And we have to implement 2 more, we discovered today. So it's crazy. But we passed the IO 500 benchmark without any problem for data and metadata. Okay. As I said, underlying, we use UCX for communication layer. We chose to use UCX instead of RPCs or MPI because we didn't want to be locked to one high-level passes interface, and because UCX is very flexible to implement synchronous, asynchronous communication, data buffering, and many other things. Okay, so below all of the application between the clients and the server, not the application and the client. The clients and the server in Hercules are implemented using UCX, and we exploit the interface that are available, choosing the fastest interface that we can use. One advantage of UCX is that for many things we have 0 copies, and that is very good for performance. And the other very good of UCX is that it's very aggressive with asynchronous communications. Asynchronous communications are very effective, and remote the memory access is also very effective using UCX. So we are using an endpoint communication from client to systems, but we have also broadcast and we have multicast, similar to the facilities we may have in a high-level MPI application, but very low level. This is basically the Hercules architecture. As you may see, we have the data with the node with the applications. In these applications, we are deploying the the Hercules front-end. The Hercules front-end is the client, basically, if you want to talk in a client-server way. And then we have data nodes with the servers, and we may have nodes with the metadata servers. As I said, we may have several metadata server nodes and several, of course, depending on the deployment required by the client. If the client doesn't say anything, we try to dimension the number of data nodes to the application requirement if we know them. And we deploy also several data nodes, okay? As you may see, the architecture of the metadata node and the data node are similar. Basically, we have a dispatcher for threads, and we are making communication using TCP/IP or InfiniBand, or depending on the protocol we can exploit. And we have a pool of worker threads that are doing the operations. Then we have a memory pool to store everything, and we have workers inside the node to deploy the operations to the worker. This way we can parallelize all the applications, distribute the applications and parallelize applications internally, and do scaling easily. The internal layout of the data is organized in the way of a data set. As I said, internally, we don't work with files or similar things. We call everything a data set. So basically, the full storage is a full data set, and inside that data set, we may have another data set. So at the end, when we deploy Hercules, we have a large data set, what we call the storage. Inside this data set, we have local data sets that are belonging to each node, and inside the local data set, we have a smaller data set that are related to the partition of the data stored in that node related to each application. At the end, you have a distributed data set. The only thing is that you are going to see the same name in several nodes with some extra information to define the data set that we are talking about. And basically for the metadata server, we are not working to the block level, we work to the data set level, and then internally we sort the names, okay? So how we can distribute the blocks in the data set is completely decoupled of the structure itself. It depends on the policy we are using for the data set. So when we deploy one configuration of Hercules for one application, the application can even specify the policy they want to use to distribute the data, and that policy will be applied to distribute the data. As I said, in our mind now we are using round robin, but can be changed easily just when we start the file system, okay? For deployment strategies, we have two deployment strategies, one that we call attach and the other is detach. The attach application means that we are deploying on each node the client and the server. So we have so many clients and servers, and they are staying in the nodes of the application. In that way, we can explore locality easily, and depending on the behavior of the application, if the application is doing, for example, writing one file per process, with this kind of application, the locality will be maximum. Then instead of using a kind of round robin distribution or something like that, we will use a policy that is called local. That means that all the information will stay in the node for that process. And we avoid a lot of data communication. We want to do that because you have seen the last computers, the ratio between computing and the network is worse every day. So we have a lot of computing nodes that are very powerful, but the network connections are not scaling a lot. So the ratio of, again, the computing capacity of one node and the I/O capacity in the network is decreasing. So it's critical to diminish the communication. And we can do that using this attached deployment. The problem with this attached deployment is that when the application dies, the Hercules deployment dies with the application. If we want to avoid that, we can use this detached application where the servers are separated from the application. And then we have the servers in different nodes, and we can deploy several applications. For example, using Slurm, we can deploy a job with several steps, and then the different steps can use the same servers without any problem. Even if one step is over, another step start, for example, in a workflow, they will use the servers, and as the servers are not killed, the information will be there. So that way, we can use those servers to exchange information between the different states in a workflow without many problems, okay? The only problem with this application detached is that we have to control the layout of the servers if we want to apply malleability, and then we have to extend and shrink the servers with an external mechanism that is not directly linked to the malleability of the application. For that, we will use again cargo and score to send the command to Hercules inside Admire and saying to send the command to Hercules and extend or shrink the features, the number of servers. Okay. Basically, this is the same thing I said. And these are basically the data distribution policies we have right now. Of course, they are just mathematics functions for data mapping, so we could even include any more. We could even think of providing a function to allow the user to specify the data distribution if they know how to do it. What would be very nice for malleability, because some application has a specific way of distributing the data. So in some cases, they know very well the data distribution, and we could provide the facility to include a function to the users to define a data distribution so that we could minimize the data mobility and malleability operations. So we have typically round robin, that is most common. Buckets means that data set has a fixed size with the same number of blocks, and they are defined as a number of chunks, and these chunks are consecutive, okay? So you have a chunk from 0 to n, n plus 1 to n, and that. So that the location of the data is very easily. Hash basically is a hash operation that is very similar to the hash operation you apply in Redis or one of these in-memory databases. And then we have a hash policy applying CRC operations over the data. This is another way of hashing. And then, as I said, we have the local policy. That is basically means that each block is staying in the node or always in the same server that the process is generating the node. In this way, if we do an attached configuration or attached deployment, we are going to be sure that the data produced locally is going to be in the same node. Of course, with the local policy, you may have imbalance, which is a major problem because one node can run out of memory, for example, and while another node is fine. The way to solve this would be to apply malleability, and if needed, to exploit this process into processes and moving the data, extending these local buffers to the two new nodes. One thing we have is in our prototype is that we have included file system malleability features. That means that we can extend or reduce dynamically the number of servers or span for Hercules, sorry. And in this case, we have a prototype that is running well. We are extending the system. And we also have a prototype now that is working when we are reducing the system. We are still testing how to reduce the size of the number of the servers, because in that case, we have to reconcile the data. Remember that we have ephemeral data. We don't have a persistent storage. So in the case of expand, basically, the things we do are easy because we don't change anything. The only thing we do is extending the number of servers and the name of the servers in the configuration files. And we start to apply that configurations, the new configuration in the mapping functions from that point beyond. So that means that our file system is not equally distributed along the time. If we apply malleability, we are going to have some files that are distributed up to here and another files that are distributed up to the new configurations, okay? If we are only working with a file or with a small number of files, what we do is that we have a portion, a chunk of the file that is with the old configuration, and from that point beyond, we have the same file extending to the many servers. For rinking the system, basically we have to be sure that we don't lose data. And the problem is that we cannot do lazy reconciliation because due to the internal intelligent controller and the SLAM configuration, if we say SLAM that we are going to remove data, SLAM will kill the nodes and we are going to lose the data. So we have to be sure that we have the data safe before killing the nodes, okay? So what we are doing right now is the easy solution. The easy solution is flashing that information to the persistent storage, and then lazily we are restoring this information in the nodes that are still alive in Hercules, okay? So that's working. It's a little slow, but it's completely transparent for the users. For the interface, we have our own API, native API library. As I told you, we are using a get set interface basically, and we create data set, objects, and some other things. We have a deployment using Fuse. We are not using it in Admire because this deployment using Fuse has all the restriction of the operating system and is very slow. And then, as the same as in Gecko or in Spine, we have using LD preload. So we are intercepting all the system calls and sending the system calls to any of the system operating system, file system, sorry, depending on the path and the mount points. To integrate Hercules with an application is very easy. The only thing we have to do, as in Gecko, is to define the mount point for Hercules, and from that point beyond, we start to write and read files in Hercules, okay? If we need initial data, also, we have to upload the data to Hercules, and then we have to work, and we need to keep this data safe at the end. We have to download the data to the persistent storage, wherever it is. File system, SSDs, non-volatile memory, something like that, okay? So we have passed the IO 500 benchmark successfully, and now we have all the applications of the project running on using Hercules, okay? And the results are nice. In here you can see the scalability in using the Torino cluster. There is a cluster we have for testing in that map. We have 64 compute nodes with Intel OmniPath, 100 gigabits per second. Okay, we are using UCX and OpenMPI. You have the configuration there. And we have, these are the results using IOR, which is a strong scalability test, increasing the number of client nodes. Again, a predefined set of server nodes. As you may see, Hercules is the red lines and BGFS has the blue line. And for right, we are increasing the scalability. Actually, as you increase the number of nodes, you can see that VGFS is keeping the scalability and decreasing when you use more than 32 nodes, even when you are writing, which is very curious because in VGFS they have a very aggressive cuts in the client, okay? And as you see, when we are reading, we are again being more scalable as we use the number of client nodes. We increase the number of client nodes. However, when we have very small, a very small number of clients, we are less efficient at VGFS. Okay, why? Because we are not using this kind of cuts. We are not doing things like prefetching, things like that. So we are trying to solve this left part of the read test better doing prefetching. Okay, we are testing now how to do and doing more prefetching and being more aggressive. For example, one problem we have is that if we use these artificial intelligence tests that are using small accesses, we are not doing things like we do in libc library, for example, that are very basic. They are getting blocks and then extracting the data from the blocks and such and such. But we are now working to optimize these results. Those are the results for the IO 500 benchmark. In some cases, we are better than BGFS. In other cases, we are better than us. Okay, but we are scaling in the similar way. Okay, so we are not losing performance. Actually, again, when we have more clients, we have more scalability on the BGFS. Be advised that this is the BGFS that we have in Torino cluster. Okay, in that computer. We have tests in another computers, for example, in Mare Nostrum, but they are not here. How to deploy Hercules? Okay, the way to deploy Hercules is very similar to the deployment you have seen in Gecko. Basically, we have a deployment of Hercules that can be done in user space. We don't need root permissions for anything. And this is the way of starting Hercules. Of course, we have a script for starting, stopping, shrinking, and expanding the system. Here is you have Hercules start. You define the configuration that is in Hercules metadata file and the data configuration that is in Hercules data file, and all this information is included in these files. Okay. So in this case, we deploy the number of data and the metadata servers, the number of data servers, and with the configuration specified here. So basically, we have the list of nodes for metadata and data, and then in the configuration, we say things like the block size, data set size, local data set size, and these kind of things. For Slam, we can also start the system using Slam, and the script is the same. The only thing we use is another different configuration. We have a configuration file that is slightly different, but you see that the deployment is very easy. Okay. And now, for the test here, if you want to do it, the people in the room or the people outside, we have implemented a deployment of Dockers so that we can deploy the system using Dockers. Okay. This is brand new. So, for example, if you have an ARM microprocessor, probably is not working because the container has been made for AMD. Okay. But you can download it. We will adapt it also for ARM. And you can download the Dockers from this from Docker Hub. You can download an Hercules server, an Hercules client, and once you have done that, you need some time to download the Dockers, but you can do it. They are available. You can execute the Dockers with this command: Docker run Hercules server. In this case, we are starting the server with an internal network and with this image, and then you can test it using the Docker super commands. For example, in the client, first thing you have to do is mounting the system. Then you can execute one test. Okay, everything is included in the image. You can see that after executing the test, you have created some files in the directory where the system was mounted. And you can also execute another test to modify the previous configuration. Okay. And after doing that, you will see that you will get the results of the IOR here. One configuration for writing, this is the first test, IOR with the same configuration for reading test. Okay, and in here you will see the files that you have created and you will get the results. Okay, I cannot execute it here because I have an Apple. So I have a new processors. And obviously, honestly, we didn't have time to to adapt it. This is brand new. But the system is also available, as you saw in Torino. And as I said, we have ported the system to any applications. So we will, of course, document it. But in case any one of you have interest, the people outside or here in the room, you can contact me or Javier Garcia Blas, and we can see how to deploy it. In Torino, we have the Spark deployment and everything prepared, so it should be easy to build everything and send everything to any software storage to recover it. And that's all for basically for Hercules. What we're doing now is that we are working on malleability. As I said, we want to minimize the operations we have to do post-ring the file system. That is the problem, and we are playing with the pools, the size of the pools, and some other features to see how we can reduce the execution of these operations. And we have to integrate in our project in Admire, we have to integrate the system with the monitoring tools that you are going to see later. That's very easy, but we have to spend some time to do it. But we right now are collecting local data, monitoring local data. So basically we are monitoring the memory bandwidth, the memory storage, the memory capacity. We are freeing each node, the network bandwidth, and some other features for the file system. One thing that we are controlling is the quality of server. And for this, what we are controlling is that if we are losing performance when we have computing peaks, okay? Basically, when you're using HPC, you deploy one application, the process of one application in the same node. It's not very usual to mix several applications in the same node, but even in some case, if the application have peaks, we may have problems because remember, we are applying asynchronous things very aggressively. So it may happen that the application has a computing peak and we are at the same time trying to do a synchronous operation over the network. So we are watching if we are degrading the quality of serving is being degraded. And in that case, what we do, obviously we cannot control the application. What we do is stopping the queues, delaying the queues to avoid harming the application, I would say, okay? So we try to overlap everything, but if we have builds, we have problems with the applications, we always try to favor the application, not our Hercules file system. And that's all on my side. Please download the Dockers. The Dockers are working well. You can download it and you can execute that sequence of tests, and the Dockers will be, you will see the results. And that's all. I don't know if there are some questions for the presentation.
There's one question.
Yeah.
Are there special commands for expand and shrink? In the chat.
In the file system, you mean?
Yes.
In the file system right now, we are controlling we have two ways of controlling the malleability for span and shrink. One is to use external commands using the script, as we saw here. You can say Hercules span, Hercules shrink, and you can say the number of nodes, okay? You could even say what nodes do you want to span or shrink with the make a host file. So that's easy. Internally now, in our prototype, we have also an internal control if we want to do it. That is, for example, in the case that we are losing performance in one or several nodes. So in that case, we can decide to span the nodes. But we can only do that if we are in a detached mode, because basically we span the servers. If we are in attached mode, we cannot do that because expanding the file system will mean expanding the application. And that we cannot do that. That has to be done using the external command coming from the cargo score, because the intelligent controller, in the case of a mine, knows how to do that. Of course, you don't need to use the intelligent controller or anything like that. If you have another kind of controller, you may have external controller, say, okay, you have to expand, you have to shrink. For that, we use the script. Okay. More questions? So this is why we have to integrate everything with the monitoring information, because we need more monitoring information to take better decisions. Okay. One thing we are doing now to finish is that we are using this IO behavior, IO traces information that we have been collected with other projects, as we have seen yesterday, and we are downloading the behavior of some of this application to decide if we have to have more information to know if we have to expand or shrink. Okay. So in parallel, we are modeling that behavior so that we can know in the next step what is the application going to do. We can be prepared. But this is still going on. I don't know if it will be provided by the end of the project or out of the project. More questions? No? Okay. Thank you then.